All right, hey guys, now we're going to go over the worksheet on periodic trends. So periodic trends actually takes what we learned last time on Coulombic attraction and just applies it to specific properties of atoms or elements, whatever you want to call it. Same thing, atoms, elements. Elements are just the categories of atoms that we have. That's all it is. Say, this atom is lithium, this atom is sodium, so on and so forth. Okay, so there's three periodic trends we're going to discuss. The three trends we're going to talk about are number one, atomic radius. Okay, atomic radius is just the size of the atom. Pretty simple, size of the atom. Okay, the second one is we're going to talk about ionization energy first. So ionization energy. Ionization energy is the energy required to remove an electron. So if we want to take an electron from an atom, how much energy is required? If you think about it, protons and electrons, they're attracted to one another, they're stuck together. It's going to require a certain amount of energy to pull it off. Okay, and that amount of energy to pull it off, we call that ionization energy. Okay, the reason we call it ionization energy is because when an atom loses or gains an electron, it turns into an ion. Okay, and in this case, when we remove an electron, we get a positive ion. It's called a cation, just like my cat here. Oh, well, I was going to show you, but he's chilling. Okay, and then the last one we're going to talk about is electronegativity. Electronegativity is a little bit harder to understand. However, it does, electronegativity is just really the pull that an atom has on an electron of a different atom. Okay, so when two atoms come together, how strongly does that atom pull on the electrons of the other atom? That's electronegativity. Okay, electronegativity really determines how atoms bond. So whether they form ionic bonds, covalent bonds, whether they form polar covalent bonds or non-polar covalent bonds, which we'll talk about actually in the next unit when we talk about bonding. Okay, so we're going to talk about each one of those things today as we go through this POGIL worksheet here. These are actually called POGIL worksheets. Pretty cool, pretty interesting. Okay, so let's read this little blurb here. The periodic table is often considered to be the best friend of chemists and chemistry students alike. Okay, it includes information about atomic masses and element symbols, but it can also be used to make predictions about atomic size, electronegativity, ionization energies, bonding, solubility, reactivity. Okay, in this activity, we'll look at a few periodic trends that help you make those predictions. Like most trends, they are not perfect, but useful just the same. So as I said, we're going to talk about atomic size, electronegativity, ionization energy. From those three things, we can actually find out about bonding, solubility, and reactivity. Okay, we're not talking about those specifically today, but from these periodic trends, you can determine a lot. So you can determine a lot about those other things. Okay? Okay, so now we're looking at the questions here. Okay, consider that on Model 1. So Model 1 is the next page here. So you'll see it, something that looks like that. It's all these. These are just the elements with some numbers below them. Okay? Each element has three numbers listed under it. Which one represents the atomic radius? Well, if you look down here at the bottom, the radius is the first number. The first number is the radius. So the first number. So for example, let's look at hydrogen here. Hydrogen, this is the radius here. So I put it in blue. That's the radius there. That's the radius. Radius, radius, radius. Okay. What unit? So the next question asks, what unit is it in? It's in picometers. PM. PM, also known as picometers. It's really small. Okay? Now, write a complete sentence to convey your understanding of atomic radius. So what is radius? Radius equals the distance from the center to the outermost part of a circle. So it's the distance from the center to the outermost part of the circle. Okay? In general, what is the trend of atomic radius as you go down? Okay? And then they want you to give 3 examples from 3 groups. So right now I can actually see 3 groups. So I'm going to put it just like this, right next to it. Okay, as we go down, what happens to the radius? As we go down, radius increases. So as we go down, the radius increases. If you look here, lithium, sodium, potassium, it goes from 152 to 186 to 227. So it gets bigger. Look at the second group, 112, 160, 197. And then the last one here, 83, 143, 122. Oh, there's an exception. Okay, like we said, not all these trends are not perfect. The trends are not perfect. Okay, there are some exceptions to the rule, and that's okay. Okay, we're not going to really worry about the exceptions right now. Okay, just in general, know that as we go down a group, the radius generally increases. So most of them follow that rule. Okay, all of the ones that I'm circling, they still follow that rule just fine. Okay, they all follow that rule just fine. Now, using your knowledge of Coulombic attraction. So, we're going to Coulombic attraction here. Explain the trend that we just explained here. Radius increases as we go down. Okay, so we're either talking about change in distance between the nucleus and the outer shell, or the change in number of protons. Okay, remember here we're adding energy levels. So as we move down, we're adding energy levels. Because we're adding energy levels, we're increasing the distance, we're decreasing attraction, the atom's getting bigger. So we're increasing energy levels, therefore, 3 dots means therefore, increasing distance and decreasing attraction. Okay? And really, atomic radius, as we're increasing energy levels, we're increasing distance, we're making it bigger. So it's kind of a stupid one for radius, just increasing. Yeah. Okay, now let's look as we go across a period from left to right. So as we go from left to right, we notice something a little bit weird. It goes from a bigger number to smaller, 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 smaller. Bigger, smaller, 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 smaller. It gets smaller as we move from left to right. I wonder why. Why does it do that? So it gets smaller from left to right. Now, why do you think that would happen? What's happening as we move from left to right? Are we increasing energy levels? No, we're not increasing energy levels. What we are increasing, though, is the number of protons. The number of protons is increasing. The number of energy levels is not. So what's happening is as we increase the number of protons, it squeezes the atom tighter and tighter and tighter. So we increase protons, therefore increase attraction. And when you're attracted to someone, what do? You squeeze them. You squeeze them tight, right? You squeeze them really, really tight. So as we increase the attraction, we increase we don't increase the distance. We decrease the distance between them. Okay, if you're really attracted to someone, you want to decrease the distance, right? So we get more attraction, less distance. And again, distance means radius. Pretty simple. Makes sense, right? So from top to bottom, we're increasing energy levels, increasing the radius. Left to right, increasing protons, increasing attraction. It's getting tighter and tighter, smaller and smaller. We're not adding any energy levels, so it's getting smaller and smaller. Okay? Next page. Let's talk about ionization energy. So now everything we just talked about is actually going to be the same for ionization energy and electronegativity. It's all based on Coulombic attraction. It's all based on either the distance or the number of protons. Okay? So, ionization energy. So using your knowledge of Coulombic attraction, explain why ionization energy, removing an electron, takes energy. Well, protons and electrons are attracted to each other. And they want to be close. They don't want to be separated. So they don't want to be separated. Okay? So protons and electrons are attracted to each other. They don't want to be separated. All right? All right. Next question here. Which takes more energy, removing an electron from an atom where the nucleus has a tight hold or a weak hold? Well, if you're holding on something tightly, is it harder to remove or easier to remove? Obviously harder to remove. So tight hold. And I'm just going to put duh. If something's held on tightly, it's harder to remove. Just simple as that, right? Now let's look. In general, what's the trend as you go down a group? So ionization energy is the one right below. It's the one right below the atomic radius. So I'm going to circle in red. So as we go down a group, what happens to ionization energy? It starts out really high, and then it gets really, really low. It becomes easier and easier to remove an electron. Okay, there's 3 examples right here. They all decrease as you go down. So as you go down, the ionization energy decreases. Down a group, IE decreases. Okay, now why would that happen? Why does that occur? Well, as we move down a group, the distance between the protons and electrons is increasing. As we go down, the distance increases. So as we go down, the distance increases, which lowers the attraction. So it's easier to remove. Now let's look at going across a period. So as we go across a period, what is the general trend? Again, there might be some exceptions here. So as we go across, if we look here, 520, 900, 800, 1000, 1402. So I'm looking at these ones here, 1314. Generally speaking, it increases from left to right. Generally speaking. Okay, you'll see that there's actually a little bit of a discrepancy between all of these groups here, and there's a reason for that. We're not going to talk about what the reason for that is. You don't need to know the reason. We're not going to be concerned with it. Okay, but as we move from left to right, in general, the ionization energy increases. Okay, left to right, IE increases. Oh, that was supposed to be for number 9. Okay, why does that happen? Why? Because as we move from left to right, are we changing the distance at all? No, we're not adding energy levels, but what are we adding? We're adding protons. We're adding protons from left to right, which increases attraction. That's simple. Increasing number of protons, increasing attraction. Is this familiar? It's the same thing for atomic radius. That's why it's so easy to if you understand Coulombic attraction, these other periodic trends are much, much easier to understand. Okay, adding number of protons, increasing attraction. Okay. Now, atoms with loosely held electrons usually classified as metals. They will exhibit conductivity, ductility, malleability because of their atomic structure. Would you expect these metals to have high ionization energies or low? So meaning they can give up their electrons really, really easily. So therefore they would have low ionization energy because they can give up their electrons easily. Okay. Low ionization energy because they give up electrons easy. If you didn't pick up on it, E minus means electron. And then IE is ionization energy. Okay. So if you think about it, metals are on the left side of the periodic table. That makes sense. They have low ionization energies. As you move from left to right, the ionization energies increase, which makes them more non-metal. Periodic table makes so much sense now, doesn't it? It's starting to make so much sense. Love it. Love it. Okay, last one is electronegativity. Electronegativity, again, is the measure of attractiveness between the electrons of one atom and the protons of another. Basically, when two atoms come together, how strongly does the other atom pull on the electrons of the other? Okay, so out of these diagrams, which one shows that? Okay, and this only happens, we're only talking about electronegativity usually in a covalent bond, so when electrons are shared. So we're looking at the nucleus of one atom attracting the electrons of another atom when they are shared. Okay, so which one of those do you think it is? It's actually B. They're sharing the electrons. The nucleus is attracting the electron that is shared. That is electronegativity. That is a visual representation of electronegativity. Okay. Now let's look at the trend. What happens to electronegativity as we go down a group? I'm going to erase some of this stuff. Makes it less confusing. Oops. I don't want to erase it. There we go. So electronegativity is the last number at the third number at the bottom there. You didn't quite figure that out already. As we go down a group, it goes from 1 to 0.9 to 0.8. So it decreases. Pretty much always decreases. Decreases. Okay, so as we go down a group, it decreases. Down, decreases. Explain the existence of the trend. Why does it happen? Well, as we go down a group, the distance increases. The distance between the proton and the electron increases. So we're increasing distance because more energy levels. Because we're adding energy levels. Okay. Now, because we're increasing distance with more energy levels, we have less attraction. So simple. Okay, now let's look across a period. So as we move across a period, we have 1, 1.5, 2, 2.5, 3, 3.5. So we're increasing. 0.9, 1.2, 1.5, 1.8, 2.1, 2.5, 3.0. Increasing. Okay? If you go down, 0.81, 1.7, 1.8, 1.9, 2.1, 2. Increasing. So we're consistently increasing from left to right. So from left to right, increasing. Okay. Now explain the existence. Well, we're not adding energy levels from left to right. We're adding more protons, which increases the attractive forces. So increase protons, increase attractive force. And just as a little side note, we're not adding any energy levels. No more, well, that was an ugly more, E levels. So we're not adding any more energy levels. Okay, now the last question here, it asks you to look at these two diagrams and figure out which ones match with which. I always like to I never memorize these trends. I always just think about them, okay? So let's think about this. We're looking at atomic radius, ionization energy, electronegativity. So on the bottom here is low and high. So for this one, we're going to have high electronegativity to the right, and it's a little bit confusing what these arrows mean. I don't like the way these are set up. They don't make much sense. So is this low to high? Is that what it means? I'm a little confused. I forget. But anyway, atomic radius should get bigger as you go down and should get smaller from left to right. So bigger as you go down. Oh, I guess this means low and this is high. And this is high. Low. So low to high, low to high, low to high, low to high. Let's just say that, okay? So atomic radius should get bigger as you go down, smaller as you go to the right. So that's this one, atomic radius. Ionization energy should get higher as you go from left to right and get lower as you go from top to bottom. So that's ionization energy. And then electronegativity should get higher from left to right, lower from top to bottom. So this is also electronegativity. Okay, but again, don't try and memorize them, try and understand them. Okay, and that is it for this one. It's a little bit tricky. There are some exceptions. We're not going to worry about the exceptions. We're just worried about the overall general trends. Okay, and that is it. I call it a day for that one too.